The linear factor theorem tells us that the factorization of the polynomial, f of x equals a sub n x to the nth power plus a sub n minus 1 x to the n minus 1 power plus dot dot dot. That means the polynomial expression continues as indicated, plus a sub 0. The factorization of this polynomial, and the polynomial has n greater than or equal to 1. The degree of the polynomial is greater than or equal to 1, and also a sub n is not equal to 0. So this first coefficient can't be 0, because if it is, you won't have this expression. If this is 0, then you won't have x to the nth, so the degree really won't be n. So that has to be the case. The factorization is f of x equals a sub n times x minus r sub 1 times x minus r sub 2 dot 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 times x minus r sub n. That means that for this general polynomial function, this would be the factorization. You want to notice that the coefficient of the first term, which is the leading coefficient, is the first number in the factorization. And then you have all your different factors for the polynomial. And then the r sub 1, r sub 2, r sub 3, these are the zeros, or the roots. So r sub 1, r sub 2, dot dot dot, or the zeros of the polynomial. They are the zeros of the polynomial. So this means that once you get a 0 for a polynomial, once you get a number that will make the polynomial 0, you just subtract that number from x, and that will give you a factor in the linear factor theorem. Now let's look at an example of how this linear factor theorem works. Suppose we want to write the factorization of f of x equals 6x squared plus 17x minus 28. First of all, we would factor this polynomial function using our usual methods of factorization. We have a quadratic trinomial here, so that means that we would get two binomial factors. When we multiply the first two numbers together, we have to get 6x squared. So here we would have 6x, and here we would have x. That would give us 6x squared. When we multiply the last two numbers together, we have to get a negative 28. And then, of course, you remember from the FOR method, you multiply the inside two and the outside two and add those together, and you have to get the middle term here. So we have to have negative 7 here and positive 4 there. That would be the factorization using the usual methods of factoring. But when we look at the linear factor theorem, we have the leading coefficient here. So the leading coefficient was 6. That means that here we have to factor out the 6. So when we factor out the 6, we have to write the expression inside the parentheses as numbers that will give us the expression that we have here. When we multiply 6 times this first expression, we have to get 6x. So that means we would have x here. because 6 times x would give us 6x. When we multiply 6 times this next expression here, we have to get 7. We have to get negative 7. So this has to be 7 over 6. And then, of course, this part remains the same, x plus 4. So now we have the factorization in the form of the linear factor theorem. We have the leading coefficient here in front of the parentheses. Then we have just plain x, like we have in the linear factor theorem, just plain x minus the one of the zeros, and this is just plain x minus the other zero. So if we put it in the exact form as the linear factor theorem, this would be 6 times x minus 7/6 times x minus a negative 4. And this would have to be minus a negative 4 because we have a positive there. Minus a negative is the same as plus a positive. If we just put minus 4, it would not be the same thing that we have in the previous step. So this would be our final factorization. Either one of these would really be acceptable as the answer for the final factorization for the linear factor theorem. Of course, this one is the one that you'll see in the answer in your textbook when you work problems similar to this problem. So that is the linear factor theorem, and that's how we write factorization in the form of the linear factor theorem. Remember, you have to have just x for the first term in each factor. That's what the linear factor theorem tells us. And then you have the leading coefficient as the first number on the outside of the, and the only number on the outside of the parentheses.